That's what it is. No kidding.
Yeah, you want to do, you might want to do it down just to make sure it's full.
Hey, students on the call, can you guys let me know if you can hear? Microphone here. Can you guys hear?
Yes.
Judy, can you let us know if you can hear? Luke? Or send a message over chat saying that you can hear? Okay, good. Yeah, they can hear. So that's great.
What you can also do in case you don't get any feedback from them, you could actually run your own test here.
Oh, we do?
And then it'll verify if something's coming out on the other end without anybody else.
Why doesn't it ask me to sign in? What is this? Let me sign in. Oh, ask me to sign in.
Maybe I'll clarify when we go to. And then they're the same time person's conversation as the same two kids. Yeah. Sam. Maybe and then go right forward. And then okay.
Yeah. Looks like everything's working. Yeah, looks like everything's working. So that's good. Thank you.
Okay,
Yeah, great.
sorry about that,
No, it's okay.
last time, but one quick thing.
Yeah.
Is I'd love to know how to get this to not pop up there. To see how it just is floating there,
Uh-huh.
so I might come over here and move this whole
Yeah.
thing
Yeah,
way down on the
Yeah.
bottom, so
Yeah.
that way,
yeah.
oh no, that's still in the way, isn't it?
No, it's okay.
Okay, well, maybe it'll be less in the way over there.
Yeah, that's 1 9 is fine. I'm
Okay.
not worried about that.
All
Okay,
right.
great. Thank you.
Well, if it ever comes up again, you know how to
Mhm.
call us.
Ah,
Now I know another thing to check. Sorry for the frantic stuff on Tuesday, but you should be good to go.
Okay. Okay, good afternoon, everybody. Well, again, sorry for the trouble last lecture, and the recording was just my voice, was nothing that was recorded as I wrote on the screen. But hopefully today we're going to be good, and from now on we're going to be good. Any questions before you guys okay doing the homeworks? Yeah, try to get the homeworks done and submit it before the deadline, so you get full points for what really you should be getting. As I mentioned last time, there's like 11 students who didn't submit the first 2 homeworks, which is pretty disappointing. Trying to help everybody, but you guys also need to help me so that we can work together. Okay, so let me, since we missed some of the stuff from last time, so let's maybe just go quickly go through the slides that we went through, and then we'll move on to new contents for today. So in this chapter, we're talking about the the earlier sections in the chapter. The last 1 or 2 sections we don't target here. So that's also something that give you guys a chance to learn if you need it. So we'll be just stop right over at maybe the applications and so on. So we started with this one. So we look at the ideal diodes. In the ideal diodes, the voltage drop across diode is 0 when it's forward biased. The current is 0 when it's reverse biased. So basically, you're looking at just 2 conditions. One is called forward bias. Yeah, this pen doesn't really write well. My handwriting is not as bad as that. There's some other, sometimes we call it on, sometimes we call it conducting. So those are the same thing, which means the diode is forward biased. When it's forward biased, voltage is 0, but current can be like anything. It's undetermined unless you have resistance and other stuff in the circuit. You can calculate how much current is flowing through the diode. And then the other one will be the other state is reverse biased. And sometimes it's also called like off. The reverse biased off is the same thing. When reverse biased, current is 0. And voltage can be anything. But usually, it's going to be not as much as it's going to break the diode. So it goes down to the breakdown region. But since it's the ideal diode, we really don't have a limit. We don't have a breakdown. We don't have like a limit of current. It's just saying when voltage is, when it's reverse biased, current is 0. When it's forward biased, voltage 0. So those are the 2 characteristics of ideal diodes. And we went through calculating the current by like looking at the right one. The diode is forward biased, 0 volt drop. So you get the current by using simply voltage divided by current, by resistance, you get current. For this one, because the diode is reverse biased, there's no current. So sometimes when we get started, students asking, how do you know it's reverse biased or forward biased? Well, what happens with the voltage across the diode? Okay. If you can make assumption to start, and of course, after you determine it's forward biased, you immediately set the voltage to 0. Okay, if it turn out to be reverse biased, we immediately set the current to be 0. Like in this case, for example, if we assume diode is reverse biased, and then there will be no current. If there's no current, the voltage about the diode in the middle, how much would that be if we don't have a current? The voltage here will be 10 volts, right? 10 volts minus 0 times 1K, that gives you like 10 volts. And then therefore you say, well, it's not possible because the diode cannot have a 10 volts drop across it. It got to be 0. So that's why you know that it's forward biased. Now for this one, you look at it, it's reverse biased, so therefore there's no current. Once there's no current, the voltage here is going to be 0 volts, right? So this is 10 volts, this is 0 volts. So when the 0 volts, you see the voltage across the diode is 10 volts, but it's in a reverse direction. So therefore, that diode is reverse biased. So that's simple ways to look at how and then we went through this one. So if you have a diode, again, ideal diode, you have a sinusoidal AC input. When voltage is positive, the diode is full. When the voltage is negative, you got diodes reverse bias. It's like, therefore you got 0 voltage. So you got half wave rectifier. Sometimes we call this half wave rectifier, and we're gonna get to that point also later. We have also do that. Now, if you have a voltage, DC voltage on the right hand, Now you have a little bit difference from the previous one because if the AC voltage, even if it is positive, you still don't have current unless the positive voltage is above the DC voltage. So if the DC voltage, if AC is 11, you still don't have current. Until AC reaches 12, that's the point it's going to start to have current. When it's more than 12, you start to have current. So that, therefore, if you look at the current, the that's also a rectifier, sometimes called like a current limiting circuit. Okay. Now, if you have a voltage source, and we had this example as well, on the in series with a diode, which means that you can get the output. You can get the output when get at the output, it's equivalent to the DC voltage, right? So when input is more than the 12 volt voltage, what do you get? You still get the DC voltage. So what we are saying that when voltage is positive, see this one here is what you get at VO. So when AC is more than 12, you got 12 volts. When AC is less than 12, you got this. Why is this? Because the diode reverse biased. Therefore, you don't see the 12 volts. You only see the AC coming in. So the AC can come through when AC is less than 12, but when it goes beyond 12, the diode is forward biased. So therefore, you will see a constant 12 volts. This is called a voltage limiting circuit. I got a couple of examples. I think we didn't go through this example, so probably can go through now. So if you look at the 4 different configurations, let's look at the top left one. So the top left one, you can see if the voltage VI is larger than 5, what do you get at the output? So if it's more than 5 volts, D1 becomes forward biased, right? So D1 becomes forward biased. Therefore, what you see at VO is going to be 5 volts. Okay. But if VI is less than -5, what do you get at VO? It's small, but it's smaller than -5. Therefore, you get D2 is going to be forward biased. Therefore, you get VO at -5 volts. But if VI is in between 5 and -5, it's not going to be now the diode will be conducting. So therefore, your output is going to be just same as VI. So if VI is larger than -5, less than 5, your VO is going to be same as VI. So this circuit, basically what this tells you is that your output is going to be something like this. So the upper limit is 5 and the lower limit is -5. And then the 3 different illustrates each one of them how this works. Like in this, it's more than 5, D1 is conducting, D2 reverse bias. So therefore, you see 5 volts. So this is 5 volts. The top graph, if less than both diode, if I is less than -5, this is reverse bias, but D2 is forward bias, -5 volts. So therefore, you got a waveform as I draw over here. We saw this example, so we probably don't have to do that. And there are a couple of examples for us to calculating the voltage and current. It's fairly simple as long as we can identify how each diode is either conducting or reverse conducting. Like the first one here, you can see if, again, when you start, when it's not, this is actually obvious. But sometimes when it's not obvious, what you need to do is make assumptions, right? So in this case, if we assume that V is, no, actually, let me see. I think I did share, right? Okay, yeah. So if you assume there's no current, you immediately get V is going to be 5 volts. So that's impossible because the diode cannot have 5 volts. Therefore, D is conducting. So therefore, you get current is going to be 5 divided by 2.5K. That gives you 2 milliamps. And you got V is going to be 0 volts. And for the second one, you can see that it's reverse biased. It's against very obvious. Because you assume it's reverse biased, you immediately get V equal to 5 volts. Therefore, that assumption is correct. Then, of course, your current is going to be 0. So the next one is a little bit interesting because we have the ground up and we have minus power at the bottom. Therefore, sometimes it might take a little bit of effort to identify what happens to the diode. You can still assume like the diode is, say, you can start with either forward or reverse bias assumption. It doesn't matter. Eventually, it will give you the same result, only because only one of them is correct. So let's assume it's in forward. So what you can start is assume it's forward. If we assume it's forward, which means you're going to have current up here this way, right? Because the diode is in the upside down direction. So if you have a current that way, how much voltage? Or is it possible to have current going up in this case? No, it's not possible because you get minus 5 volts down below and you got 0 up. The only way current flow is to flow from high voltage potential to a low voltage potential. So it's not possible. So therefore you say this is not possible. So it's reverse. And then is it a reverse correct? Because if it's a reverse means there's no current. So current, when you assume reverse, immediately you get current is 0. So when current is 0, the voltage, how much voltage do we get at the point? Now, here, be careful because there's also plus minus sign definition. So ideally, you can get the voltage, let's say called VO here. This pen is not working well. So we can get a VO is going to be minus 3 volts, right? Because there's no current. Therefore, the voltage drop across the 2.5K is 0. Therefore, VO is minus 3 volts. If VO is minus 3 volts, how much is V? It's 0 minus 3. So you got 3 volts. Okay. So that's this one. Now for the last one, if you look at circuit, it's again very obvious because 0 is at the top and minus at the bottom. So this is forward biased. So if it is forward biased, you got immediately V is 0. You got V equal to 0, and you got I equal to the 0 minus 5 divided by 2.5, same thing, you get 2 milliamps. Okay, so now we're going to have additional examples to illustrate not so obvious configurations. Okay, we'll look at both. So let's look at this one. Straight diode. They look in parallel. Yeah, go ahead. Sure. Okay, I can do that. Well, this one. Well, because there's no current. There's no current through the resistor, right? So a negative 5. Oh, 5, no 3. No, guys. 5. Sorry, sorry about that. 5. 5. Okay. 5. Okay. Yeah, sorry about that. All right, now let's look at this more complex example. Let's look at the diagram on the left. So you have 3 diodes. They look like in parallel, but not in parallel because each one has its own input. So if you have all 3 nodes tied together, that will be in parallel. But in this case, they're not. And then we do have them connected output at the same point, and then we have 1K going down to ground. So in this case, we need to identify which one is forward, or is it possible for them all forward, or is it possible for all of them in off, or cut off, or reverse biased? So that's kind of a combination. So how do we start? Well, as I said before, you can always make assumptions. So we can make an assumption, let's say to one of the diode is forward. Now, you might say, okay, why do you start with forward? Well, because what I know is that the ground is over here, and that voltage on that side is higher. So I'm pretty sure there's going to be current flowing. I just don't know which one is going to conducting. That's the idea. So let's assume 1, 2, 3. Okay, let's assume, let's give some numbers like D1, D2, D3. Okay. D1, D2, D3. So let's assume D1 is, for simplicity, I just write on, means forward biased. So if I assume D1 is on, what do I get voltage? The voltage marked between the node and then the ground. How much voltage do I get if I assume D1 is on? If we assume D1 is on, which means it's an ideal diode, which means D1 has 0 voltage drop. So that 1 volt on the left hand of D1 goes to the node, right? So we get V is equal to 1 volt. Again, this is only assumption. We have to verify if that assumption would stand or not. So if you say V1 is 1 volt, what I mean is that this is 1 volt over here. Now you look at D23, what happened to D23? You have 1 volt on the right hand, 2 volts on the voltage drop on D2 is going to be 2 minus 1 is 1 volt. The voltage drop on 3 is going to be 3 minus 1 is 2 volt. Because this is ideal diode. You cannot have voltage. It has to be 0. So which means it's impossible. And then the conclusion is that D1 cannot be on. D1 has to be off, reverse biased. And similarly, if you assume D2 is forward biased, it's going to have a problem with D3 because D3 is going to have 3 minus 2 is going to be 1 volt drop, which is not possible. So which means D2 cannot be forward biased either. So the only possibility is D3 is forward biased. So this is wrong. And only we're going to assume D3 is on. If D3 is on, we got voltage. How much voltage we get? 3 volts. Okay. So if we get with 3 volts, now we need to go back to verify. Is it okay for D2 and D1? Well, let's look at D2 and D1. So the voltage across D2 is now it's actually 3 volts. So the voltage across D2 is going to be 2 minus 3, it's going to be minus 1. And the voltage across D1 is going to be 1 minus 3, it's going to be minus 2 volts. So what I'm marking here is, you see, if that voltage across diode in the direction that I marked, plus minus this way, if the voltage is negative, it means the diodes are reverse biased. So last assumption is correct. So D3 is on, D2 and D1 both are reverse biased. So that concludes the problem. Okay. Any questions? Okay, if not, then we can move on to this one. So this one is just the flip. We have 5. Yes, we apparently can do anything we want. I mean, any assumption we can start with. So let's call this D3, D2, D1. Then we're going to have a voltage here, called V3. Here, we call V2, V1. Okay. So let's assume D3 is on. If we assume D3 is on, what voltage do you get at the node on the right hand? If we assume D3 is on, the other side of D3 is 3 volts, which means on the right, on the left, on the right hand, it has to be 3 volts. So if it's 3 volts, what happens to D2 and D1? So VD2 becomes 3 minus 2 becomes 1 volt, which is not possible. So, which this assumption is wrong. So you can start to assume, like, you can do the assumption, you can do same assume D2 is on, and you will have V equal to 2 volts, and you have VD1 equal to 2 minus 1 equal to 1 volt, which also not possible. So therefore, we have this assumption is wrong. And then finally, we have to assume that D1 is on. So if D1 is on, we have V equal to 1 volt. And then we have VD2 equal to 1 minus 2 equal to minus 1 volt. And we have VD3 equal to 3, 1 minus 3 equal to minus 2 volts. So which means this is reverse. So the reason I want to do this too is just to reflect what we did in the beginning, saying if we assume D2 is on, that's incorrect. So D2 must be reverse biased. Now we conform it. We assume D3 is on is incorrect. So D3 must be reverse biased. Finally, we got everything is correct. Are we good? Yeah? Okay. I probably, we're not gonna do more examples. Yeah. So let's start to this real diodes. So last time I already illustrated the waveforms of a real diode, or sometimes we call it spice model for diode. So the current of a diode is apparently in this region. This region is called breakdown, and the whole region is called reverse, and then this side is forward. So let's mark them up here. Got this is forward biased, and this is called reverse biased. And this region is called breakdown. And then this region here, you see the current close to 0, 1 volt is very small. can be written as spice model, which is here. I mean, it's already here, but I can rewrite it so you guys can copy it. So current ID equal to IS times e to the v d over vt, and then minus 1. So in here, we have vt is called thermal voltage, 25 millivolts. They call it thermal voltage because this vt changes as temperature changing. For semiconductor, it's at 25 degrees C, it's 25 millivolts. But if you go to 50 degree, and then that vt is going to be different than what it is at 25 degrees C. So this finally, this equation here, K times T divided by Q, and then K and then Q are some constants, and T is temperature. So when T increases, VT will increase. VD is the voltage across the diode. So VD is the voltage across the diode. So VD is, so you guys can write down. And then we have also IS. So IS has a couple of different names, and the one that we could call it like saturation current. So saturation current means that if you give enough voltage, that's only like you can get to that point, all the electrons being used, that's all the current you can get. No more than that. So that's why it's sometimes called a saturation current. Okay. So this exponential term becomes quite large when VD and over VT, because VT is only 25 millivolts, right? So VD is typically in the 0.7 volt territory. So 0.7 divided by 25 millivolts against milli, that's volts. So it's like 700 divided by 25. That gives you more like 30, 20 to 30. Therefore, e to the 20 to 30 is a much larger number than 1. So often in the future, in almost all textbooks, we would simplify ID to IS e to the power VD over VT. Because E VD over VT much larger than 1. Okay, so this is the equation we're going to use. IS times E to the power VD over VT. So at this point, we can start to do, say, examples. I give you IS, I give you VT, you can calculate ID. Or if I give you ID, IS, you can calculate VD, so vice versa. So if I want to, say, calculate VD for a certain current, what do I do? Well, basically, I say I take a logarithm on both sides. So I get like ID over IS. I take a log. And then I multiply VT, and I got VD. So basically, this is a very simple way to convert from calculate ID. Knowing VD, calculate ID is this equation, and knowing ID, calculate VD is this equation. So let me give you one more. Okay. This here, a little bit exaggerated drawing. So what I mean is that you look at this blue line, it's below like a 0. It seems that when the voltage is negative on the diode, you get non-zero current, which is not true. In most cases, you do have some leakage. Like reverse bias diode, even if it's real diode, you still have a little bit leakage. The leakage is we mostly as 0. So it's like this. And also this one, we try to to expand it to see, okay, from 0 to 0.7 volts, typically around 0.5, you start to have current. If it's below 5, the current is kind of negligible, but between 0.5, the current starts to increase. Around 0.7, you kind of get the vertical line already, and by beyond 0.7, the current increase. So that's the basic drawing. Now, a lot of the problems where you see in the homework, they will say this. This is a term that they will often use. It's a diode is said, let's say, to have at 1 milliamps. So this says something like this very often. In the book, it's got the problem is a diode is said to have 0.7 volts at 1 milliamp, or it said to have 1 milliamps at 0.7 volts. When they say this sentence, it's almost always said that the diode is non-ideal. You can no longer assume it's 0.7 volts at any current. So basically, when they tell you this, they want to ask you something else. They will say, okay, what is the you can do either from current to voltage or voltage to current. So what is the current if VD equal to 0.725 volts? Or what we can do is we can ask what is voltage VD if ID is equal to 5 milliamps, whatever that number is. I give you the diode. I know it's going to give you 0.7 volts at 1 milliamp, but now I want you to know how much voltage drop if my current goes to 5 milliamps, or if my voltage drop is 0.725, what will be the voltage drop? Or if my current goes to 0.5 milliamps, what will be the voltage drop, right? So that you can do that all the time. So this is by looking at the equation we had before, is looking at ID equal to IS e to the VD or VT. And of course, VT is, you can assume it's the room temperature, so VT is going to be, so that is something has to be given, otherwise you will not be able to solve. So knowing ID is 1 milli at VD, I can write 1 milliamp equal to IS e to the power 0.7 divided by 0.7 divided by 0.025. Like I mentioned last time, that 25 is milli. So a lot of students make a mistake by plugging out 25, which makes the current really, IS really big or really small. Yeah. So it's small, yeah, really, yeah. So if we plug in 25, the IS becomes a very big number, a very small number. Sorry. So if you look at this, you got the right hand, the left hand is given, the right hand also pretty much given. You can easily calculate IS. So you can find, so from here you can find IS. And if you have a calculator, and you can basically, I mean, IS is just 1 milli divided by this e to the power 0.7, 0.025. Right? You can get this. But sometimes, in fact, you don't have to calculate IS. You can use some comparison because, let's say, so number one, so they wanted to have the current of 0.275. So what I'm looking for is ID equal to, let's call it ID2. maybe I just call it ID1. Will be equal to IS e to the power. So VD is given at 0.725 over 0.025. So I want to find the ID1. Ideally, you can simply plug in IS to this equation. You will be able to get that ID1. So that's one way to do it. But I can also plug in the equation of IS in a way that, okay, so let me write it in this form. So let's say ID equal to IS times e to the power VD over VT. And then I have ID1 equal to sigma IS times E VD1 over VT. So I can, for this two equation, I can take the ratio. If I take the ratio, I would have ID1 over ID equal to, IS will cancel. So I have e to the power VD1 over VT divided by e to the power of VD over VT. So I got this. Now this one, you know that this is e to the power, which means it's going to be like e to the power VD1 minus VT divided by VD over VT. And that further can be written as e to the power VD minus VD1 or VD1 minus VD. And this ID1 over ID. So we have this equation here. Now from this equation here, I want to start from here. So I can say ID1 equal to ID times e to the power VD1 minus VD over VT. So in this case, we don't have to calculate the IS. VD1 and VD, we got a little bit easier. You don't have to actually write down the exact number for IS. If you want to find the voltage, like if we give for problem number 2, so this is problem number 1, right? So for problem number 2, I am given ID, therefore I can write ID2 over ID equal to e to the power of VD2 minus VD divided by VT. Now I can take a logarithm on both sides. Therefore, I have VD2 minus VD divided by VT equal to log ID2 over ID. And from here, you can say VD2 is equal to VT times ID2 ID, oops. Times log ID2 over ID, and then plus VD. So we have two equations here. So one is if you were given current, you can get the voltage. And for this equation here, if you were given voltage, you can get current. You can calculate current. So this is a very you guys are going to see a couple of questions in the homework are asking for this. So given a voltage and find the current, given current and find the voltage, using that definition of a diode is said to have 0.7 volts at 1 milliamps. Okay. Any questions? You guys doing okay? All right. So this one example, let me see. I have to bring up I forgot to write down the exact given conditions. Let's see. Let's see. Give me 1 second. But the idea is that you will given your diodes. One diode T2 is connected to ground, and T1 together is to assume the ideal diode. Okay, we're going to go with if it's not ideal, what happens? I just need to know what they say about the conditions of the diode. See 2.3 or 4.2. Okay. So guys, you can start working on it to look at what happens if those diodes are ideal. Can you find the voltage across I2? And can you find the current in each branch? Actually, oh, this is a video example, so it doesn't show in my book. Okay, that's fine. I'm probably going to just make up some numbers, so it may be different from it is in the book, which is going to be okay. So let's one way. Let's do this. Assume idea. So if we assume it's an ideal diodes, it means that let's look at D2. So there's current 10 milliamp coming down, and there's 3 milliamps coming through D2. So if we look very simple 3-node circuit. So there's 3 milliamps coming down this way. And 10 milliamp coming from the top. And how much is going down through D2? It's going to be 7 milliamps. Okay. Well, this assumption actually is correct, whether it's diode is ideal diode or non-ideal diode, it doesn't matter because they have to do it this way. Because otherwise, there's 7 million. So D2 cannot be reverse biased. If D2 is reverse biased, you'll have trouble because that 10 milliamp current has nowhere to go because there's only 3 going down. And you violate circuit theory. So D2 has to be forward biased. And also D1 cannot be reverse biased. Because if D1 is reverse biased, that 3 milliamp current doesn't have any way to go. So it has to go through D1. So therefore, both diodes are going to be forward biased. So that's something that we can conclude. But the only difference between ideal and non-ideal diodes is that in ideal case, if D2 is forward biased, what would be the voltage across here? Let's call it V1. How much is V1? If D2 is forward biased. The bottom of D2 is a ground, is 0. So the top of D2 is going to be 0. Okay? So if V1 is 0, and what is V then? Because D1 is forward also biased. So V is going to be 0. Because the top of D1 is 0, D1 is forward biased, the bottom of D1 has to be 0. So it's ideal diode. Okay? So that's number 1. Number 2, we're going to assume a piecewise linear model. You guys remember what we said? Piecewise linear model is if it's forward biased, it's going to be 0.7 volts. That's what we said, right? Okay. So in this case, D2 forward. So what is V1? No, it's no longer 0. Oh, 0.7. Yeah, okay. Yeah, great. I heard 0, sorry. So it's 0.7 volts because D2 is forward biased. It's a piecewise linear model. It got 0.7 volts drop. So between ground and the diode, this is 0.7 volts. So V1 is 7 volts. And D1 is also forward biased. So at the bottom of D1, how much is it going to be? D1 is forward. So therefore, V is going to be V1 minus Y minus 0.7, because D1 has 0.7 volts drop because it's forward biased. So the top and the bottom of D1 has 0.7 volts difference. The top is 0.7, so the bottom is 0. So that's the case with piecewise linear model. So now let's look at non-ideal model. So in the non-ideal model, we have to give some condition. So in this case, I'm gonna give you a condition also. So 1 milliamp at 0.7 volts. Again, this number may not be the same as it is in the book. So don't be surprised if you see the answer here is different. But I'm not going to be able to get the answer anyway. I have to have a calculator. So I'm just going to write the expression. So 1 milliamp at 0.7. I'm going to have to recall the expression for current, which says ID equal to IS e to the power VD over VT. And VT is 25 millivolts. So that one we have to give it to you, otherwise you can't find it. So from here, of course, you can plug in that 1 milliamp, plug in that 0.7, you can get IS. So that's one way to start is you get IS equal to ID over e to the power VD over VT, which is 1 milli divided by e to the power 0.7 divided by 0.025. So yeah, that's some value you can find. So once you find S, IS, we can find now we can find voltage. Well, how do you find voltage? Well, first of all, current is given here. So 3 milliamp is given. So which means the current through D1 is 3 milliamps. So I can say ID1 is 3 milliamps. Right? So that is given. That's the current source through it. So if ID1 is 3 milliamps, I can calculate also ID2. So ID2 is going to be 7 milliamps, because that's really, regardless of what type of diode model you use, you're going to get the same current. So if we know ID2, I can calculate V1. V1 is going to be IS times e to the power of, no, I cannot write that. What I'm wanting to say is, let me use a blue color. So I can use ID2 equal to IS e to the power of VD1 or VT. And from here, you can get VD1 equal to VT times log ID2 or IS. Yeah, so we got VD1. VD1 equal to, VD2. Because VD2 is related to ID2. So we have VD2 calculated. So VD2 is equal to, in this case, it's equal to V1 that we had. So let's write down. So that's equal to V1. Now we can also calculate VD2. So from ID2 equal to IS over times VD2. Oops, now I had a also mistake here. So this should be VD2. So this is going to be VD1 ID1, ID2. I'm going to calculate ID1 equal to VD1 over VT. So from here, we can find VD1 equal to VT times log ID1 over IS. So finally, we can find V. V is the voltage about the current source. How do we find V? V is the voltage about the current source to ground. So if we know V here, we know VD2, VD2 is V1. So V1 minus VD1 gives you, or if you still have doubt, you can say, so V1 minus V equal to what? You can always, like, if anytime you have extra doubt of what you do about, which one is positive, which one is negative, you can always use this equation. A high voltage potential minus a low voltage potential gives the voltage difference. So the voltage difference between V1 and is VD1. So which means V1 minus V equal to VD1. So V1 minus V is VD1. We already found VD1. We already found V1. So therefore we can have V equal to V equal to V1 minus VD1. And in this case, you can plug in these two numbers and you can get the actual numerical value for the output. Okay. And you probably want to find out that this is not so much different from 0.7. I mean, not so much different from 0. It's just slightly like different because the previous one got a 0, right? But now it's going to be because the 7 milliamp on D2, so VD2 is going to be larger than VD1. So VD1 is 3 milliamps. So VD1 is slightly less. Therefore, you will have slightly, let's say it's 0.7 minus like 0.65 or something. So the voltage here is slightly more than 0. It's not, but it's pretty close to 0. Even though the reason why is it close to 0, because that, if you recall the curve, it's pretty vertical. It's around 0.7. So it's just a little bit higher than 0.7. And the current changes, when the current changes pretty much a lot, the voltage doesn't change very much. So it's always near 0.7. Okay. And we talk about the temperature dependence of diodes earlier, just briefly mentioned. This actually gives you the exact flash when you have two temperature T1 and then this is T2. And when T2 is, when voltage increases, you can see the whole thing shift this way. What it means that for the same voltage, for higher temperature, you get higher. So if I draw a vertical line, here. This is the voltage. Like at a lower temperature, I get only this much current. But when temperature increases, I get that much current. Okay? That's what happens. When temperature increases, the current through the diodes will increase for the same voltage. Or in other words, for the same current at a high voltage, at a high temperature, you will have less voltage drop on the diode. Yeah, so this example, similarly, okay. I guess one of the questions is that if the diode is not ideal, like if it's an ideal diode, in this example, it would have been very easy. So this one pass, no current. So current is 0. And voltage, if current is 0, voltage is also. So I just want to stay here for one more minute. Is that yes, some students make a mistake saying that maybe like 9 volts. So that is a mistake can be made just because you didn't pay attention. The reason is because 9 volts. Well, put it this way. If you have 9 volts here, you would have current. If you have a resistor, it has to be 0. 0 means no voltage, right? So this voltage 9 volts. Okay. So next example is going to look at, let me see what next slide about. Yeah. So for circuit like this, when the diode is ideal, it's very easy to do. When the diode is not ideal, we have to plug in the equation that we had earlier. So again, we're going to solve this circuit using like 3 different approaches. So we're going to again give you a condition saying 1 milliamp at 0.7 volts. So this is the given condition. So when the diode have 1 milliamps, the voltage drop is 0.7. But even though that is given, but I want to still to do 3 cases. So one case is ideal, and 2 case is piecewise linear model, and 3 case is non-ideal. Okay, so we want you, I'll give you a resistance of R going to be 1K, and VD is going to give you 10 volts. So in ideal case, apparently VD 0 and also forward, right? So you guys see it's forward, right? So that's easy to see because the voltage goes through the VD. So therefore we have I equal to just voltage divided by resistance, 10 divided by 1, give you 10 milliamps. So that is ideal diode. But if it's non-ideal, if it's piecewise linear model, the diode will be still forward biased, but the VD is going to be 0.7 volts. So if that VD is 0.7 volts, we will have I equal to V minus VD over R. That gives you 10 minus 0.7 divided by 1K. That gives you 9.3 milliamps. Okay, so finally, it's a non-ideal model. If it's a non-ideal model, we can use loop equations. In this case, why we use loop? It's no node, it's just one loop. So in the loop analysis, we have VDD equal to I times R plus VD. Because it's a non-ideal model, we don't know I, we don't know VD, we don't know either one. So therefore, for only giving VDD and R, we are not able to solve for either I or VD at this point. So how do we do that? Well, we know one thing for sure from the earlier study is that VD is, or ID equal to, in this case, ID is same as I. So ID equal to IS times e to the power of VD over VT. So if we plug in the second equation to here, you will see that you have now replaced I with VD. You have replaced I with VD. One VD. But of course, we have to solve for VS. How do we solve for VS? No, IS? Well, because we know that 1 milliamp is equal to IS times e to the power of 0.7 divided by 25 milli. So that equation is kind of a given condition. So we can find IS. So find IS, plug in this one to here, you will have VDD equal to IS e to the power VD over VT plus VD. And here, so you only have, because VS already solved, therefore you only have one variable, VD. But you might think, I don't know if you guys can solve this use a graphical calculator, you probably can do that. But if you don't have a graphical calculator, it will be very difficult to solve for VD because the nonlinear component over here. But fortunately, we have a method called graphical method. Yeah.
The IS power B nothing multiplied by R.
Yes. Yes, you're right. Thank you. Okay. So fortunately, we can do a graphical analysis. In the graphical analysis, what we're doing is we can plot the two equations on the same graph, and we look at the cross point. So the two equations we have, one is VDD equal to I times R plus VD. The other equation is I equal to IS times e to the VD divided by VT. So what we are doing is here, we're going to plot current. Let me see what they want. Is, yeah, okay. We're going to plot current I as a function of VD in this diagram. So let's look at equation number 1 and equation number 2. So for equation number 1, what is the relation between current and voltage VD? Well, it's very simple because if V is 0, you get I equal to VDD over R. So VDD over R is when VD is 0. So VD, so when VD is 0, we get the point here. It's a line, it's a linear. So we got this one here is VDD over R is this point over here. And then when I0 here, you got VDD equal to VD, right? So that's this line here, but this line here. So we got this line is, so this is VDD. So we got that line. So that's one. And then for equation number 2, we already know what this is about, right? You guys remember what this is? This is the line where you start from 0 and then around 0.7 you start to increase very quickly. So really what you're saying is this is equation here. Oops. Yeah, maybe I draw this. So if we draw that red line, that's equation number 2, then you will be able to get the cross point. You will get VD, and you have ID. Because there are 2 equations, right? You plot them on the same graph of the 2 equations. This equation 2, equation 1, the cross point is a solution. And this solution is going to be same as if you use your graphical analysis. I mean, your graphical calculator basically does the same thing. You put the equation in there, they will give you a solution. Actually, it does this. The procedures of this one is illustrated here. They give you some names like load line, diode characteristics, and you got the cross point of the 2 lines. You get the solution. So we talk about the we already dealt with we mentioned this. So is also called it's called constant voltage model. This one, like why it's called constant voltage model? Is forward bias voltage. Linear model. We should draw that also on the same graph. Is this one here? Okay. A, B, C, D, E, F. So last one here, really, you cannot replace that with a voltage source or an open circuit, nothing. So you really cannot, you have to be a diode. So this is a constant voltage drop model. Whenever it conducts, we use 0.7 volts. When we use it open circuit. And the voltage has so that's okay for constant voltage model, sometimes called a piecewise linear model. Now here, another example. What we're doing here is we'll look at this one as 3. Again, we're going to do 3 different. We'll have time. Yeah, we have a few minutes to finish this problem. We're going to also do 3 cases. So 1, 2. So 1 is idea. 2 is the constant voltage model, and 3rd is non-idea model. So in idea model, you can see it's 10 volts at the top. Through a resistor goes through 3 diodes going to ground, which means all 3 diodes must be forward biased. And then your voltage VO is going to be how many volts? Do it together. It's an idea diode. 10 volts. Is that correct? I heard 10 volts. I also heard somebody say 0. Is it 0 or 10? Okay, well, because I heard 10 first, so let's look at it. Is it possible to have 10? If it's 10, what happened to the 3 diode? You got 0 here. You got 10 volts across diodes, idea diodes, which is supposed to be 0. Possible? Therefore, it's not 10. It has to be 0. Of course, you can calculate current. It's going to be 10 over R. All right. Second one, constant voltage drop. Yeah, apparently, you don't have to really do too much. You know that these 3 diodes are going to be forward biased. Each one is going to have 0.7. And how much is the total? It's going to be 2.1 volt. And your current is going to be 10 minus 2.1 divided by R. Okay. Last one, nonlinear. Nonlinear model or non-ideal model, nonlinear model. If it's a nonlinear model, we don't know the current and the voltage, but we do know the equations we can write is 10 volts equal to I times R plus 3, well, not 3. In this case, it's just VO. VO. But we can also know that VO equal to 3 VD. And we know that ID and VD has a relation, or in this case, we simply use this I, no D's, just I. So I equal to IS e to the power VD or VT. Each VD gives you the current of each diode, and 3 diodes in series, so they have the same current. Now, of course, we have to write that 1 milliamp equal to IS times e to the power 0.7 over 0.025. I mean, that is given is 1 milliamp at 0.7 volts, or sometimes they say 0.7 volts at 1 milliamp, same thing. So from here, you can go here, and from here, you go here, and from here, you come here, and you can find basically the equation, nonlinear equation. Again, it's hard to solve. So you want to do a graphical analysis, we can do it 10 volts, this is 10 over R, and you have this one. This is, remember, this is a this line over here, VD, not just VD, because you have 3 diodes, okay? You have, oh, sorry, this is, no. Give me, sorry, I'll correct it. I wrote it wrong. So it should be I equal to IS e to the VD or VT. Okay, but this the VD is 3. What I want to say is ES is VD is VO over 3 or VT. That's what I want to say. Okay. So you plot these lines and you find the cross point that gives you a solution. Okay. Any questions? Okay. Monday, the next week. And remember, we have a exam on Thursday, but I want to remind you, bring your ID. You can bring your student ID, the best. If you don't have your student ID, bring your driver license or something, passport, something that we can verify your picture. And when you do the exams, we would like you to drop your bags on the side, your phones on the side. You can keep your laptop and your writing pad for your work, but putting everything off on the side. Now, yeah. Yeah. And also, our TA has office hour tomorrow. I know nobody came to my office hour yesterday. If you guys want to go to the TA tomorrow for the office hours, go to EIS 104, so he's going to be there for you guys. Okay? All right, bye.
Bye.